Welcome to the video Help with Physics Problems for Physics 1B. In this video we're going to be covering Homework Set 2, Part 2, which is everything under the heading Capacitors and Dielectrics. For 1221 students this is questions 6 to 10. For 1231 students this is questions 9 to 16. Problem 6 for 1221 or 9 for 1231. In this problem we have a parallel plate capacitor. There's a voltage difference of 100 volts between the plates. There's a distance, d is equal to 1.0 millimeters between the plates. Each of the plates has a radius of 8 centimeters. And because it's a capacitor, one plate has a charge plus Q and the other minus Q. We're asked to find this Q. So for a capacitor problem, the normal way to do it would be to use the formula C is equal to Q over V. But the problem with this formula is that unless you've memorized C for a parallel plate capacitor, you don't actually know what C is. C for a parallel plate capacitor is given by epsilon naught A on D. So if you want, you can use this, but you would need to memorize this. So let's not do it that way. Let's do it by using the formula that the change in voltage is equal to ED. Now, this is assuming that we have a constant electric field, which is the case between two charged plates as long as the separation is small. Okay, so what we need to do is try and work out the electric field so that hopefully the electric field will be able to give us information about what Q is, because we've got this and we've got this. Okay, so use Gauss's law. The E dot dA is equal to the enclosed charge over epsilon naught, and we'll just consider this one capacitor plate here. Let's draw a cylinder. So this is our enclosed charge in here. So the enclosed charge, let's let this little cylinder have a radius capital R. So we've got pi r squared, that's the surface area, and then times the charge density over epsilon naught. And the charge density in this case is just given by Q over A, where A is the surface area of the capacitor. And for a cylinder like this, it's only the two ends of the cylinder which will contribute, as E dot dA is 0 everywhere else. The electric field and the surface area elements are at right angles to each other, whereas for the two endpoints, they are aligned. So we've got that the E dot dA is equal to the electric field times 2 pi r squared, because we've got the two ends of the cylinder, each with surface area pi r squared. Okay, so looking at these, we can cancel out the pi r squareds, and we end up with our electric field is equal to Q over 2A epsilon naught. This is for one plate. But here we have two plates. The electric field will add together in the middle as the electric field lines are going in the same direction as these two charges have opposite signs. So for two plates, it's Q over A epsilon naught for both plates. So now we've derived our expression for the electric field, we can substitute it back into this equation. So we've got the voltage difference between the plates is Q over A epsilon naught D. And so solving this for Q is equal to the voltage difference A epsilon naught on D. And so this is 100 times the surface area of the plates, which is pi times 0.080 squared, times epsilon naught, 8.85 times 10 to the minus 12, over the distance between them, 1.0 times 10 to the minus 3. And solving that on the calculator, you end up with 1.8 times 10 to the minus 8 coulombs. You can see if you substituted this into here in the first step, you would end up with the same formula. Problem 7 for 1221 or 10 for 1231. In this problem we have a series of capacitors. We have C1 and C2, literally in series here, C1, C2, and then we've got C3 in parallel with the C1, C2 combination. And we're asked what is the equivalent capacitance? Okay, so what we need to do is just work out the equivalent capacitance of C1 and C2, and then we can work out the equivalent capacitance of this with this. Okay, so 1 over C, let's call it 1 and 2, is equal to 1 over C1 plus 1 over C2, as these are in series, and this is the formula for equivalent capacitance in series. So C1, we're told in the question, is 10.3 microfarads. C2 is equal to 4.80 microfarads, and C3 is equal to 3.90 microfarads. So 1 over C1 and 2 is equal to 1 over 10.3 times 10 to the minus 6 plus 1 over 4.80 times 10 to the minus 6. So solving this on the calculator and remembering to invert it, we end up with C1 and 2 is equal to 3.27 times 10 to the minus 6 farads. Okay, so now C1 and 2 are in parallel with C3. So C total is equal to C1 and 2 plus C3. So this is equal to 3.27 times 10 to the minus 6 plus 3.90 times 10 to the minus 6. And solving this on the calculator, we end up with 7.17 times 10 to the minus 6 farads, or we could write it as 7.17 microfarads. So that's the answer to this problem. Problem 8 for 1221 or 11 for 1231. Okay, this is a bit of a complicated setup. We have a capacitor here, C1, with positive charges up here and negative charges down here. It's then connected through a couple of switches to capacitor C2. We have another switch here. This is C2, which is the other way up. It's got its negative charges here and its positive charges here. And here's point E, here's point F. And C1 has a capacitance of 1.16 microfarads. C2 has a capacitance of 3.22 microfarads. And initially, the voltage across them is equal to 96.6 volts. So each is charged to this voltage and then they're connected up like this. Now switch S1 and S2 are now closed and we're asked to find what's the potential difference between E and F. Okay, when this switch is closed, what's going to happen is these negative and positive charges are going to flow together and they're going to cancel out as much of the charge as it can. So what we need to do is we need to work out the initial charge here and the initial charge here, and then we'll be able to do that to work out the total charge once the switch has been closed. Once we've got the total charge, we can use C is equal to QV on V to work out what our voltage is going to be, as we can work out the total capacitance for this situation. Okay, so let's work out initial charges. Okay, so Q1, the charge on capacitor 1 initially, will be equal to C1V, which will be 1.16 times 10 to the minus 6 times 96.6. Solving that on the calculator, we end up with 1.12 times 10 to the minus 4 coulombs. Q2 will be C2V, so that will be 3.22 times 10 to the minus 6 times 96.6, and so solving that we get 3.11 times 10 to the minus 4 coulombs. So the negative charge here will cancel out all the positive charge here. So C total will be 3.11 times 10 to the minus 4 minus 1.12 times 10 to the minus 4, and so that will be 1.97 times 10 to the minus 4 coulombs. So after these switches have closed, we'll have a negative charge up here of 1.97 times 10 to the minus 4 coulombs and a positive charge on these two plates of 1.97 times 10 to the minus 4 coulombs. So this is the combined charge. This will be split between these two plates, and this will be split somehow between these two plates. Okay, so we've got the total capacitance now that the switch is closed. Sorry, this is the charge. We've got the total charge now that the switch has been closed. So what we need to do now is work out the total capacitance. Well, C total, these are in parallel, so it's just C1 plus C2. So it's 1.16 plus 3.22 times 10 to the minus 6. And so solving that on the calculator, you should get 4.38 times 10 to the minus 6 farads. Okay, so we've got C and we've got Q, so we can get V. V is equal to Q total over C total, which is 1.97 times 10 to the minus 4 over 4.38 times 10 to the minus 6. And so solving that, we get 45.4 volts. So remember, E will be negative and F will be positive. And then part B says, what is the charge on C1? So we've worked out the total charge distributed between these two. We've got C1 plus C2 is equal to this, but now we're asked to find just C1. What we can do is just go back to this equation, because now we've got the voltage difference across C1. As these are in parallel, they've both got the same voltage difference across them. So Q1 is equal to C1V, so that is equal to 1.16 times 10 to the minus 6 times 45.4, and solving that we get 5.27 times 10 to the minus 5 coulombs. C, we need to now get the charge on capacitor 2, so we can either subtract this one from the total charge, 1.97 times 10 to the minus 4, or we can just solve this equation for C2. When we do that, either way, we get 1.46 times 10 to the minus 4 coulombs. Problem 9 for 1221 or 12 for 1231. In this problem, we have two capacitors. Let's call it C1, which is a capacitance of 2.0 microfarads, and C2 with a capacitance of 8.0 microfarads. These are connected in series, and then a potential voltage of 300 volts is applied across them. Part A says, what's the charge and the potential difference across each capacitor? Well, when capacitors are connected like this voltage is going to induce a charge on the capacitor plates. When capacitors are in series, you can see for this section, any charge which moves from here has to end up here. So these two capacitors actually have to have the same charge. So the charge on each capacitor is the same. So we have Q1 is equal to Q2. And we can use C is equal to QV. Now we've got the total voltage. We can work out the total capacitance, which will tell us the total charge, which is the charge here and the charge here, which will be equal to the charge there and the charge there. So let's work out the total capacitance. Now these two are in series, so to find the total capacitance we have to use 1 on C total is 1 on C1 plus 1 on C2. So that's 1 over 2 times 10 to the minus 6 plus 1 over 8 times 10 to the minus 6. Solving that on the calculator, we end up with 1.6 times 10 to the minus 6 farads is C total. Okay, so now we can get the total charge. Q total is equal to C total V, which is 1.6 times 10 to the minus 6. This is the total V as well, times 300. And so that is equal to 4.8 times 10 to the minus 4 coulombs, and that is equal to Q1 and Q2. So we've now got the charge on each of these capacitors. Now we're also asked to find the potential difference. So V1 is equal to Q1 on C1, which is 4.8 times 10 to the minus 4, over C1, which is 2.0 times 10 to the minus 6. Solving that on the calculator, we end up with 240 volts. Now V1 plus V2 have to add to give us the 300 volts, so that tells us that V2 is equal to 300 minus 240, so that's the 60 volts. So that's the answer to part A. Part B, we now reconnect these charged capacitors but with their positive plates together. So let's draw a diagram. Here's C1, here's C2. We've got positive plates connected and negative plates connected. Now, as they're connected like this, you can see the voltage across each capacitor must be equal. So we've got V1 is equal to V2. So these charges will redistribute between them, but so that they satisfy this relationship. Okay, so V1 is equal to V2. We can use this equation up here to rewrite this as Q1 on C1 is equal to Q2 on C2. The other thing we know is that the charge on this plate plus the charge on this plate has to be equal to the total initial charge. So Q1 plus Q2 has to be equal to 2 times 4.8 times 10 to the minus 4, because this is the charge each of these plates initially has, and this charge is just going to be redistributed. It's not going to be created or destroyed. Okay, so let's call this equation 1 and this one 2. We can rearrange 2 to write Q1 on C1 times C2 is equal to Q2, which now substitute in from C1. Q2 is equal to 2 times 4.8 times 10 to the minus 4 minus Q1. So moving Q1 over here, we've got Q1 is C2 on C1 plus 1 is 2 times 4.8 times 10 to the minus 4. Now C2 on C1, that's equal to 8 on 2, so that's 4. So this is 5. So this tells us that Q1, this is 4, plus 1, that's where our 5 comes from, is equal to 2 times 4.8 times 10 to the minus 4 over 5, which, solving on the calculator, we end up with 1.92 times 10 to the minus 4 coulombs. That's Q1. Now Q2, we just have to substitute in here. Q2 is equal to 2 times 4.8 times 10 to the minus 4 minus Q1, which is this. So Q2 is equal to 7.68 times 10 to the minus 4. Now let's just use a little bit of space here to answer the final part. We're also asked to find the voltage in this situation. So we know that V1 is equal to V2, and we know that this is equal to Q1 on C1. So just substituting in, we've got 1.92 times 10 to the minus 4 over C1, which is the 2.0 times 10 to the minus 6. So solving that on the calculator, you end up with 96 volts, and that'll be the same as V2. Okay, so that's the answer to B. In part C, it says what happens if we connect them so that they're positive plates and negative plates are next to each other. Well, they initially have the same charge. So what's going to happen is this positive charge will cancel out this negative charge, and so our charge will end up being 0. And so because we've got no charge, we'll have no voltage. So everything is going to be 0 in case C, as those charges will redistribute and cancel each other out. Problem 13, which is for 1, 2, 3, 1 only. Okay, so we have a capacitor here. It's charged by a battery and then it's disconnected. So it's got some charge on each plate. Q. We then put a dielectric slab in between the plates. And we're asked to describe qualitatively what happens to the charge. Well, putting a dielectric in here isn't going to move charge from one plate to the other, so Q remains the same. We're asked to explain what happens to the capacitance. Well, C, dielectrics are designed to increase the capacitance, so C will increase. Then we're asked what happens to the potential difference. So we have C is equal to Q on V. If this is remaining constant and this is increasing, then the voltage must decrease. So voltage decreases. To the electric field strength, E is equal to Vd in a constant electric field, which is what we have in here. We're not changing the distance between the plates. This is decreasing, so the electric field decreases. And finally, to the stored energy. U, which is equal to Q squared over 2C. Q squared and 2 will remain constant. C is increasing, so U will decrease. Problem 14, which is for 1, 2, 3, 1 only. Okay, here we have a dielectric with ER is equal to 2.8. And it can withstand an electric field strength of up to 18 times 10 to the 6 volts per meter. And we place this within two capacitor plates with area A. And the capacitance of these parallel plate capacitors, one has charge plus Q, one minus Q, the capacitance is equal to 7.0 times 10 to the minus 2 microfarads, and the potential difference is equal to set to be 4,000 volts. Now this is the maximum electric field they can withstand, so we're going to need to work out what electric field we have inside the plates here. So we're going to have to use Gauss's law, but to do that we're going to need to know what charge is on each of these plates. So we know the capacitance when the voltage is 4,000 volts. So we can use this to work out the charge. Q is equal to C on V. So that's equal to 7.0 times 10. Now this is micro, so that's times 10 to the minus 6. So that's times 10 to the minus 8 over 4,000. So solving this on the calculator, we end up with 2.80 times 10 to the minus 4 coulombs is our charge on each of the plates. Now we need to consider the electric field. Let's consider it just for one of these plates to start with. Using Gauss's law, we have E dot dA is equal to Q enclosed over epsilon naught, and the enclosed charge in this case is Q over A times, if this has a radius capital R, pi r squared, and then we've got our epsilon naught, and this is equal to, we've got a constant electric field, so that's E, and the area, we only need to consider the ends, as through this part the electric field and the surface area are perpendicular, so they do not contribute. So this is 2 pi r squared. The 2 comes about because of the two ends. So rearranging this, we've got our electric field is equal to Q over A epsilon naught and 2. And now this is just for the one charged plate. We've got two charged plates, and between them the electric field lines are acting in the same direction, so they add together, and because they've got the same magnitude Q, they've got the same magnitude, so we need to times this by 2. And now what we've done is we've put our dielectric in here. So the dielectric effectively modifies our epsilon naught by the factor of this dielectric, which is 2.8. Okay, so we now have an expression for our electric field, and we are told what the maximum electric field is. So we should now be able to substitute everything into this expression to find our area. So our area will be equal to Q over E epsilon naught times 2.8. So Q is 2.80 times 10 to the minus 4. Our electric field strength, our maximum, which will give us our minimum area, is 18 times 10 to the 6. Epsilon naught 8.85 times 10 to the minus 12. And then 2.8 is our dielectric constant. And so solving that on the calculator, we end up with 0.63 meters squared. So that's the minimum area for those plates. Problem 15, which is a 1, 2, 3, 1 only problem. In this problem, we have a parallel plate capacitor. It's got area A and it's filled with two dielectrics. One has a dielectric constant epsilon R2 and one has a dielectric constant epsilon R1. So each of these dielectric constants takes up an area A on 2. And we're asked to come up with an expression for the capacitance of this setup and then to consider the limiting cases. First of all, we need to justify considering it as a parallel arrangement. Okay, so clearly it's parallel because the charge which is coming in as current can choose to either go on this part of the capacitor or this part of the capacitor. So there's two possible paths. We can get the electric field set up here or the electric field set up here. So this is a parallel arrangement as the charge coming in as current can go to either half of the capacitor. Okay, so we'll need to use the formula C is equal to Q over V. And considering these two in parallel, we can put the C total is equal to C1 plus C2. If we call this one 1 and this one 2. Okay, so we need to work out Q1 and V1. Let's start by working out V. So V is equal to ED, the electric field times the distance, assuming that it's a constant electric field, which it always is inside the capacitor. So to work out the electric field, let's imagine a prism with surface area little a on the ends. When we use Gauss's law, we only need to consider these ends because these are the only parts where the surface area increments and the electric field are aligned. Elsewhere, they're perpendicular to each other, so the dot product is 0. So Gauss's law tells us that the E dot dA is equal to Q enclosed over the epsilon naught. The Q enclosed is the surface charge density times the area over epsilon naught, and this is a constant electric field, so we can pull it out the front of the integral, and then the surface area that we're considering is the two ends of this cylinder, so this is 2A, or prism, it doesn't have to be a cylinder. Okay, so solving this, we've got E is equal to sigma over 2 epsilon naught, and this is with no dielectric and for one plate. Okay, the other plate, if this has a positive charge, this has a negative charge, so the electric fields add together within here. So the total electric field is equal to sigma, and then we double it, so we get rid of this 2 over epsilon naught. And the dielectric, this modifies this epsilon naught, so this becomes epsilon R1 for this first one, and for the second one we have E2 is equal to sigma over epsilon naught epsilon R2. Now these sigmas are different. We have Q1 on this plate and Q2 on this plate, so we can write sigma, the area of this plate is A on 2, so this is equal to Q1 over A on 2, so that's A epsilon naught epsilon R1, and then the on 2 becomes a 2 up the top. And we've got the same thing here, 2Q2 over A epsilon naught epsilon R2. Okay, so V1 is equal to just this D. This is our D here, it's on the diagram. So we've got 2Q1 over A epsilon naught epsilon R1 D, and these voltages actually have to be equal. This is equal to 2Q2 D over A epsilon naught epsilon R2. Okay, so substituting this one into here, we end up with Q1 on V1 plus Q2 on V2. Okay, so we're running out of space a little bit, but let's substitute this V1 and this V2 into this formula here. Let's make some space here to do this. So now we're substituting in to Q1 on V1. So we've got Q1, now V1, we've got 2Q1D, and then the denominator here ends up the top, A epsilon naught epsilon R1 plus Q2 on V2. So Q2, now V2, we've got 2Q2D, and A epsilon naught epsilon R2 is equal to the total capacitance. Now the charges will cancel out, and so we end up with the total capacitance is equal to A epsilon naught over 2D outside of epsilon R1 plus epsilon R2, which is what we were asked to show. We're then asked to consider the limiting cases. So let's consider if epsilon R1 is equal to epsilon R2 is equal to 1, i.e. there's no dielectric here, then in that case we have C total is equal to A epsilon naught over 2D side of 1 plus 1. This cancels with that, and we have A epsilon naught on D, which is the case for a parallel plate capacitor with no dielectric. So that is in agreement with what we predict. Okay, if we have some more room, let's try it over here. Another limiting case is if, say, epsilon R1 is equal to 0. In this case, no electric field can be generated in here, so this part is effectively not there. So in that case we have the capacitance is equal to A epsilon naught over 2D epsilon R2, which is the same as the formula for a capacitor with an area A on 2 and a dielectric epsilon R2. So that is what we would expect. Finally, if we just set epsilon R1 equal to epsilon R2, then we end up with C total is equal to, well, 2 epsilon R1, so these 2's will cancel out, and we'll end up with A epsilon naught epsilon R1 over D, which is the case for a parallel plate capacitor with an epsilon R1 as the dielectric constant within it. So this is in agreement for the limiting cases. Problem 10. For 1221 or 16 for 1231. In this problem we have two capacitors of 2.0 microfarads and 4.0 microfarads connected in parallel across a 300 volt potential difference. And we are asked to calculate the total stored energy in the system. The stored energy is given by a half CV squared, and we can either work it out for each capacitor individually and add it together, or we can do it for the total system. So the total stored energy is a half times the total capacitance times the total V. This V is the total V, it's also the V across C1 and C2. Now as these are in parallel, we have the total capacitance is equal to C1 plus C2, which is 2.0 plus 4.0, 6.0 microfarads. So just substituting everything in here, the total stored energy is a half times 6.0 times 10 to the minus 6 times 300 squared. And solving that on the calculator, we end up with 0.27 joules. So that's the answer, and that's the end of this set.